So first we're going to talk about how atomic radius varies across the periodic table, and that's its trend. So it's what it's doing overall across the periodic table. But before we talk about that, we have to say, well, what is atomic radius? What do we mean when we say that? And just like a radius of a circle is the distance from the center of the circle to the edge, that's the same thing for an atom. It's the distance from the center of the atom, the nucleus, out to the outer edge. Now, we can't say it that simply in chemistry because, of course, it's chemistry and we have to complicate everything. But there's no outside boundary on an atom. There's no fence on the outside of the boundary that says, hey, the atom's ending right here. So in order to measure atomic radius, we take two atoms of the same element and put them next to each other, like this. And the distance between the two nuclei measures the diameter. If we take half of that distance, we have the radius. So now in chemistry, instead of a simple definition of a radius like in math, we have to say the atomic radius is 1/2 the distance between the nuclei of two atoms of the same element when the atoms are joined. That's all that's saying. It's the same concept as math, but now it's looking at an atom which doesn't have that outside boundary. If I graphed the values for atomic size, it would look like this. If you notice, the yellow circles here are all group 1 elements. So looking at your periodic table in the corner, or if you got one of yours and you have it handy, this first column here, those group 1 elements, you have lithium, sodium, potassium, rubidium, and cesium all represented. And then if you look at the blue here, you've got some noble gases or group 18 elements. You've got helium, neon, argon, krypton, and xenon, and they're represented. As you can see, as you move down the column, the radius increases. There's a general trend going upward or a positive slope. Same as you move down the column for group 18, there's a general upward tick. As you go across the period, so as you travel from lithium to neon, there's a general downward trend or a negative slope. And so what that tells us is atomic size increases from top to bottom and decreases from left to right. So another way to look at that is this. The size generally increases to the right, or sorry, the size generally decreases to the right, and the size generally increases as you move down. So if a handy way to look at it, like I like to, is I like to draw just a little sketch in my notes, like this gray box here of the periodic table, and I draw just a really big circle near francium. That's the biggest radius on the periodic table. And then I draw a tiny little circle over here in the top corner by helium, and that's the littlest radius. Why does this work? Well, if I look from left to right across the periodic table, every new element as we move across has one more proton, which makes the nucleus one more proton stronger, or one positive charge larger. So what happens is now that that nucleus has a bigger charge, it pulls those electrons in tighter and it makes the radius smaller. If I look top to bottom, every new period or every new row has a new energy level, which is a whole nother shell outside of the nucleus. So now there's actually more space being taken up with each new shell, and as you move down a column, the radius gets larger.
Okay, the second trend is in something called ionization energy. You probably remember from earlier in the year that an ion is an atom that has gained or lost an electron. So the first thing that we're going to do is define this, and ionization energy is going to be the amount of energy required to remove an electron. Okay, so what you're going to have to be able to think about is what type of atoms are going to want to give up electrons, what type of atoms are going to want to gain electrons. So even though it appears to be a really big word, you know all this from the beginning of the year. Think cation, think anion, and this is going to begin to make sense. The difference here is that when we deal with ionization energy, we're always removing. So if you remove one electron, the energy required to remove that is called the first ionization energy. Okay. So if you remove a second one, we call that the second ionization energy. Remember, when you lose an electron, you become a positive ion or a cation. So when you remove an electron, you get a positive 1 charge. If you remove the second electron, you're going to get a positive 2 charge. Okay, so this is a table that has kind of showing you different amounts and different amounts of energy. You can kind of see that the unit there is joules, which we know is energy, and our good old friend the mole is coming back. But as we move forward, this is the table that's really important. As Ms. O'Reilly was pointing out with atomic radius, we have the same exact elements here. The difference you probably are noticing is that the noble gases are very, very tall on the list in blue. So you have helium, neon, argon, krypton, xenon, okay? And on the bottom, you have your group 1, your lithium, sodium, potassium, rubidium, and cesium. So what you can probably notice here is that as you go across, the noble gases have the highest ionization energy, and the group 1 metals have the lowest. Okay, so here are our trends. If group 1 has the highest, sorry, I lie. If group 1 has the lowest and the noble gases have the highest, you're going to see that ionization energy increases as you go across. And again, think about it. If you look on the left of the periodic table, these are all metals. Metals want to lose electrons. These over here are nonmetals. They want to gain electrons. So it's going to be really, really hard to remove an electron from, like this is in this box, or fluorine really wants to gain an electron. So it's going to be really, really, really tough to remove it. Second, as you go down a group, as Ms. O'Reilly said, the atoms get bigger. Think about something like francium. It's in row 7. It has 7 energy levels. Its electrons are really, really, really far away from the nucleus. It's going to be quite easy to grab an electron off of francium than it is to grab an electron off of lithium. So what happens is the ionization energy actually decreases as you go down a group. Okay? So, and as Ms. O'Reilly kind of pointed out before with the same chart, so fluorine over here is going to have the highest ionization energy, and francium is going to have the lowest. Again, fluorine is the smallest atom that we're talking about here, so it's going to be really, really hard to remove an electron from something that is small, and francium is really, really big. It's going to be really easy to grab it. Francium's like, I don't know the exact number anymore, but it might be like 87 electrons. It's pretty to grab one off of it. And again, finally, here is the trend and the explanation. So going from left to right, the energy required to move an electron increases. Why? Because elements want to, the ones on the left want to lose electrons, the ones on the right want to gain electrons. So again, metals want to lose, non-metals want to gain. So that's why as you go across, you're going to have an increase. Going down, what's going to happen is you're going to have the bottom, the ionization energy is going to go down because the atom itself is getting bigger and it's going to be easier to remove it. Secondly, we know from last week, as you go down a group, you're going to actually make yourself more metallic. Okay, so if I'm just going to look group 14 here for 1 second, carbon's a non-metal. Silicon and germanium are metalloids. Tin and lead are metals. So if you think about it, what's going to happen is the more metallic you are, the lower the ionization energy you're going to have. The more non-metallic you are, the higher it's going to be. And I'm going to toss it back to O'Reilly. Maybe.
Yep. Hello. So now the third trend, the last trend that we're going to talk about, because you're probably feeling tired already, is trends in electronegativity. So what is that? Electronegativity is the ability of an atom, of an element, to attract electrons when the atom is in a compound. So if you would imagine a covalent bond where the electrons are shared between two atoms, the atom with the higher electronegativity is like the stronger atom, the stronger element in the tug of war between those electrons. Those electrons are going to be more attracted to the atom that has the stronger electronegativity. So in general, this decreases from top to bottom. and it increases from left to right, which is the same as ionization energy. And here's a chart to show you some values that represent electronegativity. One thing to keep in mind with this is that we tend not to include the noble gases, group 18, in this trend. And that's because noble gases have their full outer shell. So they're stable and they don't really want to give up, or they don't really want to be part of a bond because they already have their full set. Now we know that some noble gases can form bonds, but remember, these are trends. These are things that happen overall, not all the exceptions. So again, as you move across the periodic table, the energy increases, and as you move down, it decreases. And this is for electronegativity. I don't know why it says ionization energy. And for here, in this top corner, notice I put an X through the noble gases. That's because we're saying, yep, we're not including those here. It's going to be biggest at fluorine and lowest at francium. And this is for electronegativity. So why does this happen? If I look from left to right in a row, I'm noticing that there's more valence electrons. And there's a tendency for the electrons to be there's more attraction for electrons towards the right. So there's a tendency to pull in more electrons when you're almost full. So fluorine is going to have the strongest pull on the electrons because they really want to be full. They're only missing that one spot. On the contrary, the beginning of the row, the group 1 elements only have one valence electron. So it's really likely to give that away. So that's going to show that you have a very low electronegativity because it doesn't want to take in anymore. In fact, it really just wants to get rid of that one. And then as you move down the row, you're still going to see that electron shielding, where each new energy level is a shield against that charge from the nucleus. Remember, it's the positive charge from the nucleus that's going to draw on the electrons to begin with. So if you have more energy levels shielding the nucleus's charge to pull in those electrons, it's going to minimize that pull. So the further you go down on the periodic table, the further you go down in a group, the less likely they're going to pull in electrons because they have more shields blocking that nuclear charge from pulling the electrons in.
And to sum it all up, what's going to happen here is we have our 3 trends, and what's going to happen here is my computer froze. Okay, sorry about that. The biggest thing to recall here is, again, that we have variations in atomic structure. What we want you to remember from all of this is that the atomic size is going to play a role in all of this, and whether an atom is a metal or a non-metal is going to play the biggest role. So with radius, as you go across, they get smaller. You go down, they get bigger. Now think about that. So that means on this side, the non-metals are generally smaller than their metal counterparts. About ionization energy, what's going to happen is, think about it. Metals that were bigger, it's actually going to be easier to take that electron, whereas the metals are smaller. They're holding onto the electrons tighter. So that's why ionization energy increases as you go across, and it decreases as you go down. In addition, remember, non-metals want to gain electrons, metals want to lose electrons. And then finally, electronegativity. The trend is identical to ionization energy, but the definition is almost the exact opposite. But if you think about it, fluorine really wants to gain an electron. So its ability to gain an electron is much greater than francium is. Francium is so big and so metallic, it wants to lose the electron. So again, what happens here is you have a decrease in electronegativity going down and increase going across. And that sums up periodic trends.